So a good talk should focus on one thing and should properly motivate it, and this is not going to be a good talk. So with no motivation, I'm going to launch into writing some code, and then I'll back up and maybe tell you a little bit about why I wrote that code. I'll go off on several divergent paths and talk about other stuff because I want to talk about it. It's cool. And then at the end, I will deliver what I promised, which is we're going to make a planet using procedural content generation, and we'll ray trace it all in real time. So a lot of graphics content development is made by artists and programmers and writers explicitly creating everything in the world. They envision it, they place every rock, every leaf, they paint them, they write the dialogue for every character. And so that's sort of mainstream content creation. And what we're going to talk about today is doing something completely different, where instead we create the rules of a universe and the initial conditions, and we allow everything else to arise from those rules. So this is not mainstream graphics, but I think it actually is the future of graphics, and so more important, more interesting. So I'll start by creating a universe right now. And as I promised you, in the beginning of any graphics program, you have formless void, you have a black screen. And in my coordinate system, this will matter in a second, I'm going to put 0, 0 at the lower left, 1, 1 at the upper right. Here, maybe we throw some examples. And so this is sort of the upper quadrant. And then I'm going to write a little graphics GPU shader program. And if you're not familiar with a shading program, I need to tell you just a few things. So float is a real number, something with a decimal point. So the int, there's a color class that has red, green, and blue RGB fields. Points are going to be 2D in this case because they're on the screen, so X and Y. And what you don't see is that wrapping this main image function are 2 for loops that iterate over every X and Y, and they run that to compute the color of that pixel. And that's sort of part of the standard full screen graphics shader setups that's implicit. And that's it. That creates a universe. That's a set of rules. And here it is. It's very boring as a universe, but it's all mine. And I'm going to share it with you. And then what I would like to do is, into my formless void, let there be some light. So I'm going to change my program just a little bit by saying, hey, at every pixel, I'll compute a sky color. And then X and Y, I've aligned the code that shows you how I compute those from forward. That's just going from pixel coordinates into that 0, 0, 0 to 1, 1. What's the interesting thing is the code on top, and all that is just different gradients. It's just functions that go from 0 to 1, but they're scaling at different rates with different exponents, so that I'll get a color gradient instead of just gray. And when I run that, here's what I get. So now my universe is a little more like computer graphics. I have a different color in every pixel. It's a little bit more interesting. And it's sort of pretty, but it's also still a little bit boring. There's not much there. So let's divide the Earth at the bottom from the sky at the top that I've already rendered. This is sort of a megalomaniac color. And what I'm going to do is I'll say that there's a line at y equals 0.5, 0.45, do a little below the midpoint. And that's just going to be a horizontal line, and that will be the silhouette of the terrain. If you're below there, it'll be black, and above there, you'll have the sky color that I already had. Now we're getting somewhere. I have, in a sense, I've created it as promised, a procedural planet. It's just it's a flat planet, first off. But this is a good start. Now we can start to make a more interesting function than the constant y equals 0.45. So what I'm going to do is I'm going to change the terrain height to instead be a noise function. And a noise function in this context is essentially a hash function. I'm going to take that real number and I'll turn it into a different real number. I'm going to turn it to 1 in this case that's on 0 to 1. But it'll do it in a stable way. So it's kind of like a random number, except every time I give it the same input, I give it the same output. It just wiggles around. And so the terrain height, I don't want to wiggle at every single pixel. It will go crazy. It'll just be jumping all over. So what I'll instead do is inside the noise function, it rounds off x to the nearest integer. So I'm a little bit shifty here, but I'm only going to see 2 heights because I'm on a unit interval. So if I see something rounded off to an integer on that, I'm only going to see sort of 1 change in value. So here's the particular noise function I'm throwing at it. It's that hash function. And then I'm actually evaluating the hash function at both ends of the interval, and I'm going to average the message. So there it is. So now I've created a terrain. And I now kind of have full control. I can set the value at every pixel. I can separate the sky from the ground, and I can control the ground with a function. Now all I need is to get an interesting function for the ground. And you can kind of squint at this and say, well, it's like a, it's a cityscape. Great, we're done. And then that's sort of part of art is getting the viewer to buy into and hallucinate and interpret the image in an interesting way. But I haven't quite given your imagination enough to hook on there, so let's do a little more. So this is where the real fun starts. Now that I have this framework, I can plug in different height functions. So what I'm going to do now is I will just take those two boxes and I'll linearly interpolate instead of the nearest neighbor interpolate. So instead of snapping to a value and changing in integer points, I'll just connect them smoothly. And if I do that, well, it doesn't look like a city anymore. It looks like a very low resolution kind of 3D scene. It's very computer graphics, this perfectly straight line. But we're sort of getting there. We have a hill. And to make it look a little less artificial, I'll replace that linear interpolation with a curve. I'll just take a function of a line and I'll change it to a function of a third order polynomial. And then this happens to be a polynomial where these constants are here to make sure that it kind of goes from 0 to 1. But when I do that, it'll smooth out the curve. And this looks a lot more natural. So now I have a pretty nice structure, and I can make things that sort of look natural, but they're just not very interesting. So let's make it more interesting. What I'll do, and this is a common signal processing field, this is harmonics in music, this is Fourier analysis, mathematics, is I'll take the noise function, and it has a certain wavelength, a certain frequency which is repeating, and what I'll do is I'll add variations on it that have increasingly higher frequencies with smaller magnitudes. So here's the low order detail, and I'll add some higher frequency detail on top. In this case, I'm going to add 5 octaves. I'll just have 5 noise functions I'm adding together. And now we have something a little more interesting. And if I just keep making that for loop go higher, maybe 10 orders, now this sort of starts to look like the silhouette of a mountain. And not bad. We're still at about 20 lines of code. I've hidden most of the main stuff that wasn't interesting. But now let's really have some fun. So what I can do is go back to the main function. And instead of saying I just have this one terrain function, I'm going to pick a sea level. And I'm going to throw just a sine wave at sea level. That'll be the tops of waves. And I'll say, well, the silhouette of the terrain, that happens at whichever is higher, sea level or the mountains themselves. And so if I draw in my sine wave sea level, I get that. You can imagine I could animate that and go visual into the show. And then I can just keep adding sort of new functions. Like maybe I'll add a very high frequency sine function. It kind of looks like the silhouette of some tall trees. Right? And maybe the Greek island going on. Now this is interesting. At this point, I have built up, just from some simple mathematical functions, a little framework, I've built up something that maybe gives your imagination enough to grip onto and say, oh yeah, like this is actually kind of some interesting terrain. I can imagine playing around in that world. But what I promised you was that I wouldn't create the world, that I would create the rules of the universe, and the rules of the universe, in this case with the noise signal as input, would create the world. And the problem is, I basically did that, except I did it by looking at the thing and tuning the constants the whole time. So one of the things I would love to have for procedural content is the notion of I can create a world that I, the creator, can explore and be surprised by. That there'll be things that I didn't explicitly put in there and anticipate. And I can do that very simply because I take this, right, I tune it looking at one particular screen, but none of these functions were limited on the x-axis to 0 to 1. That's just what I happen to be rendering by default. So if I do this, if I just shift the x by some function of the current time in seconds, then it'll scroll through the world, and I can see all of the parts that I didn't create explicitly at all, that I didn't tune the constants for. And I can see interesting stuff there. So let's do that. So here's, I went to a website called Shadertoy. I typed in exactly the code I showed you, and it makes the program I showed you. It's where I got the screenshots from. And all I'm going to do is allow time to animate. And so now what we're doing is we're exploring the world I've created. And I haven't seen any of this before. Now I actually have an interesting world from about 10 lines of code, and I'm just exploring. I'm just exploring And I can find things, and maybe there's surprising stuff that I didn't know about. You know, waves are animating and all kinds of interesting stuff, and there are trees. Can trees grow in the middle of the waves? I don't know. I didn't even think about those rules. So this is our goal. This is procedural content generation. This is probably the simplest and most accessible example you can get into. And what I did is I put all the code that I showed you on that webpage. You can just get to that from the slides after the talk. They give you links to everything. So I'll put the PDF up online on my website, capitaleffects.com, and then you can look at that shader code and you can start to change the worlds. You can create, you know, maybe you want to have boats on that ocean. Maybe there should be temples on these islands. Maybe there should be creatures all around. You can actually do all of that within this room. The quote up there is from one of my favorite conceptual artists, followup, who was really essentially an undergraduate math fanatic who somehow disguised himself as a very successful artist and made a lot of money by selling permutations, essentially. But he has this wonderful quote about conceptual art. The idea becomes the machine that makes the art. And that is the essence of procedural content generation. We would love to create, we would love to be artists, we would love to explore. Maybe we're not that great at drawing, but gosh, can we program and do math? And so we can use machines to create the art for us that we can't create with our hands. It's the ultimate paintbrush. So that was the procedural content. There's a lot of interesting things out there going on today with procedural content. You're probably familiar with some of these games. Those are the kind of results I want to achieve today. They're rich content. They have, effectively, the scope is limited only by the numerical precision of the machine. You need all kinds of variations. In some of these cases, there are little pieces like the characters, the textures of individual boxes that are hand-created. But the overall design of the levels and the planets and the characters and creatures on them, that's all procedural. If you play No Man's Sky, even if you worked at Hello Games as a developer, you would encounter planets that you didn't realize your system could create. That's a wonderful thing. It's a terrible debugging situation, but it's a really wonderful thing in terms of creating interesting art, creating essentially meta art. And I'm pointing out these specifically because they do what we're going to do today, which is create a landscape, create a planet. But there are all kinds of things. You can, as I mentioned earlier, Dwarf Fortress was just kind of the ultimate procedural game. The world, the characters within it, the histories, the backstories, the names of the characters, the poetry and music, everything in the world is created procedurally. So every time you play the game, it's a completely new universe from some very high-level meta rules. These are more concrete, down-to-earth things, but all of these are sort of within the scope of what you can do. And what's really important, and is probably a technology you've heard of, is machine learning. And I think the forefront of content creation and procedural content creation is combining the ideas of sort of classical grammar-based and noise function-based content creation with machine learning. And today, it's mostly indie games that are pushing really hard on this because they can't afford to have 100 or 1,000 artists working on a project. This is a great way for a few programmers and a few artists to create large amounts of content. In the future, though, I think there's going to be a need for all games to have visual richness, sort of down to the millimeter scale, which you just can't afford to paint, and then whole worlds and planets and universes. In order to satisfy that, I think all game studios are very interested in this kind of content creation and driving it by machine learning so that artists can create exemplars of the world they want rather than creating every piece of the world. Is a great way to magnify the intellect of the artist while taking advantage of sort of their uniquely human skills. So this isn't coming from nowhere. It's not that there's no role for an artist. It's that we'd like to amplify artists and give them much more powerful tools. Here's a general strategy for procedural content. You take some input signal. The procedural part's in the middle. You expand that input signal. You somehow amplify it, pull all this detail out of the initial state. And then the key is to interpret that in an interesting way. And every one of those boxes has to be tailored for the specific task at hand. One nice example is this program called Houdini by a company, Side Effects, that's in Toronto, founded by Waterloo alumni. And this is an example from someone else's tutorial, but it's showing a procedural city created using Houdini. And so all of this content, and effectively you can make many, many different cities from the same program are generated essentially by an algorithm. And the way that works is that it starts with some initial state. It's kind of just seeding the system, saying some areas are a little bit different than others, maybe randomly it can be painted. And there's a grammar in the computer science sense. So if you've heard L systems, formal grammars, or game of life, it's that kind of a thing. And then there are explicit geometry instances. So this program knows ahead of time about balconies and windows and doors and streetlights. And what it's choosing is how to combine them. And the rules for how to combine them are the syntax of that grammar. And that's a very classic technique for procedural content. There's been a lot of research work showing how to create sort of different styles of buildings. Trees are another fantastic example to do with grammars. Anything that has self-similarities, you can write a set of mutually recursive rules to create the world. But that's only one way to use the recipe. And here's another recent example. So this is from my colleagues at NVIDIA research program called GoGAN. And you can actually try it online after the talk. And what's happening here is on the left, the artist, right, which is like me in this case, this is the level of landscape that I'm able to paint by hand. It kind of looks like Microsoft Paint or something. But I say, yeah, there should be some grass at the bottom, some water, and a waterfall. I love waterfalls, and a tree, right? So you put all those down, and then what this program is doing is, this is, again, a generative adversarial network. So it's essentially two machine learning programs. One trained to say, hey, that's a nice photograph, and one trained to say, well, I'm going to make a photograph other machine learning program thinks is nice. And together they learn how to synthesize images. And so you feed it this kind of paint by numbers image, and then it produces a nearly photorealistic landscape for you. And as you change the little aspects of the scene, the image on the right will change. So that's another form of procedural content generation. In this case, instead of a grammar, it's using machine learning for the expansion step. And instead of a random initial state, you're painting roughly where you want things to be. And in this case, it interprets the output directly as pixels. So there is no 3D scene in GoGAN. It goes straight to the final image. No Man's Sky starts with something closer to a random scene. And it uses something called fractal Brownian motion, which is a really impressive sounding name for essentially what I just showed you, which is taking noise functions at different wavelengths and adding them together. It's called fractal Brownian motion because it happens to be a generative way of producing a random walk path that is called a Brownian motion for like a molecule bouncing around in a gas. So it happens to give you essentially a random walk, but in a way that you can deterministically evaluate it at a point rather than having it computed from the starting conditions. And there's lots of other options. So essentially, this is a generic formula, and you can take one of each of those boxes and plug it together and make a nice procedural content system. Now, the talk is full of a bunch of slides that I'm not going to really show you, but that are there for you afterwards to look through and follow links that sort of walk you through all the details about, oh, you should look up this keyword, and that'll lead you to a wonderful set of literature on how to follow it. So we need to know how to draw a procedural model before we can generate the procedural model, because otherwise you can't debug it, and I can't show you any examples. So for the initial drawing, it was pretty simple. I just said if we're below a certain elevation, then I'm going to make everything black. But I want to make something more like No Man's Sky, where I see a full 3D world, and there's colors. And so for that, I have to talk about rendering. And rendering essentially is ray tracing, sort of the way that modern rendering works. And what I mean by that is that if you think about how computer graphics works in general, I have a virtual camera that I put into my 3D scene. And it has a bunch of pixels, and then there's a lens on the front. And for any given pixel, it sort of looks out through the lens. If you imagine the lens being small, there's sort of a ray of light that would have come through the lens to the pixel. So if I just follow that ray backwards, I'll find a point in the scene that was coloring the pixel. And then I might need some extra rays to find out how much light is there, are there shadows, things like that. The core operation that we performed was tracing the path of a light ray and finding where it hits the scene. So that's ray tracing. It's sort of a core operation. The jargon on this in computer graphics is a little slippery. So ray tracing is both the name of the tracing the ray to find the surface, and it's also the name of some complete rendering algorithms that use that primitive level. There are some other words that you would hear about in, say, an intro graphics class, like rasterization. And those are essentially special cases of how do you ray trace when the rays happen to have something on top. But this notion of trace the path of a light ray into the scene, that's sort of the mainstay of most computer graphics rendering today. And what you need to know about ray tracing is that there's essentially two main algorithms for implementing it. One of them deals with explicit surfaces. So in this case, I have a scene, and when you see something like this side on the left, this is the underlying data structure. There's a mesh of triangles that happen to have some colors on top. And I say it's an explicit geometric representation because in the program I explicitly have a surface. So I have those triangles, and an array of the triangles makes the mesh. And when you want to render with explicit geometry, it's very simple. You just take the explicit geometry of the ray and the explicit geometry of the scene, which in this case is maybe four of the triangles, and you just find where the ray hits the triangle. And that's the dominant way that rendering is done today. And that's kind of wonderful because people have taken inbuilt hardware. So there's the NVIDIA RTX cards, but there's also wonderful libraries for lots of platforms that you can use to sort of not write any of that code yourself. So they're incredibly fast. In this case, these can trace billions of rays per second. So by computer science numbers, that's a pretty good number. And it's debugged. So you just go out, you instantiate the library, and it works. That's not what we're going to do today, of course. The reason I'm not going to do that is because that works with explicit geometry. And it turns out that's fantastic for ray tracing and for the rendering. It's not great for the modeling process. It turns out it's much easier to deal with the opposite of explicit geometry, which is implicit geometry. So implicit geometry, instead of saying, here is the scene, it's defined by these triangles, you can say, well, at any point in space, I'll give you a function that tells you how far away you are from the surface. So the surface is never explicitly represented, but you can sort of implicitly find out where the surface is by going to your ray. And in this case, this is called the sphere tracing algorithm. You say, how far am I from the surface? It says 1 meter. You say, thank you. You walk 1 meter and say, now how far am I from the surface? And it says, well, now you're half a meter away. And you think, well, wait, I went 1 meter, I should be at the surface. And it didn't tell you which direction. So you're wandering around, and you're saying, am I close here? Yeah, you're close. And then I can walk the distance, and I might have been walking away from the surface. But if you iterate with this, it's kind of like if you remember Newton's method or some root finding, you can eventually walk along a ray and find out where the surface is without passing through it because you know how far you're allowed to walk before you hit the surface. So if you extend that into an algorithm, you get this lovely ray tracing algorithm that works on implicit geometry. And the key idea is the same as the first example I showed you. I showed you originally a function that tells you how high the terrain is, which is essentially saying how far is the terrain from the bottom of the screen. Now in 3 dimensions, I'm going to create a different function, and that function just has to say how far away the surface is. Let me give you an example. Here's a sphere. I chose a sphere because it's the absolute simplest surface to find the distance from, because all the points on the sphere are the same distance from the center. And here's the distance function for a sphere. Just say, hey, I'm at point P, the sphere has center C, I'd like to know how far away I am. And the answer is, well, it's how far are you away from the center of the sphere, and then subtract off the radius. This function happens to have the property that it's positive when you're outside the sphere, 0 on the surface, because you're at 0 distance from the sphere, and on the inside it goes negative. We don't so much care about what happens on the inside of the sphere because you're inside of the sphere at that point. But what's lovely about that is it means the derivative of the function is continuous, so the derivative is nicely defined everywhere. And that'll turn out to be a nice property later. I'm not going to go into it, but I'm going to depend on it. So, okay, well that seems easier than coming up with a bunch of triangles, but the real payoff when doing procedural modeling for implicit surfaces is that you can combine surfaces in very elegant ways because you just write a function that calls 2 other functions and combines them. So for example, if I have 2 spheres, and I want to say, well, the distance to the whole scene is I compute the distance to the blue sphere, and then I compute the distance to the cyan sphere, and then I say whichever one is closer, that's the distance to the sphere. So I compute those two distances, and then I take whichever one's closer. And so that's great. I can take the union, but here's the lovely magical part. I can create all kinds of funny functions that combine things. I don't have to just take the min of two distances. So in this case, I'm combining them with this function. It's a little garbled by the production right now. I'll just restart it so you can see more clearly. The details of that function actually don't matter super much. The interesting thing about it is that it's just kind of this funny polynomial. But it has the property that it creates kind of a smooth minimum. So the surface defined by these two spheres, instead of being just the two spheres jammed together, is this nice smooth blob. And that's lovely for creating organic surfaces. So for creating characters, and foliage, and terrain, that's the kind of merging you want, where you can smoothly run things. And it's controllable. So I could make it a sharp corner, I could make it bow out, I could make it bow in. So that's a lovely property for combining functions. So I think I'm like 2 tangents deep now, right? From things where I've just gone off and talked about something else because I wanted to. Here's the last one, and then I'll give you a plan. There's this website called Shadertoy. And there's 2 things about the website. One is the website, the technology behind it, and the other is sort of the community around it. And there are various so-called demo scenes for different platforms, everything from Amiga, calculators, Windows PC. So the Shadertoy website happens to be one platform on which people create interesting graphics demos in elegant ways. And it happens to be a lovely one because it's online, so anyone can access it. You can use it even on a computer where you can't install anything. And it happens to have a really nice comment section with a community that sort of helps people out and praises you. So to give you some idea of what's going on in Shadertoy, I just want to show you a couple examples. So this is by Inigo. He's one of the 2 authors of Shadertoy. And he made this snail shader. Now, I mean, Inigo worked at Pixar and Oculus, and the guy's a genius. So you're not going to go off and do this tonight. I'm not going to go off and do this ever. But you could make like my Greek Islands or something tonight. So you could get it. It could be the next thing. But this is all procedural. You can see he's using all these smooth blending functions to get the complicated shape of the snail. And so this is all from a shader where you have the full source code for it. So you can look at everything he's doing, you can kind of reverse engineer it and learn from it by modifying. Here's a little bit simpler one that might be more accessible to us. So it's simulating some blood cells. And these are basically toruses that have been kind of smoothed out in an interesting way, and then put into a tunnel. I'm just trying to show you the variation of things you can accomplish with these implicit surface techniques. So instead of just any old noise function, you might start with a function that's a fractal. In this case, these are iterated function or escape systems. And so it's computing essentially a set and showing you the surface of that set, which happens to have sort of a fractal dimension, so infinite detail between 1D and 2D. You can make representational things. And this is kind of closer to our procedural goals. Right? So this is sort of a Venice-inspired scene. And because of the ray tracing, we get all this shading and lighting and stuff. But all these buildings are created procedurally. Nobody placed them, nobody designed the path of the canal. It's just coming out of noise functions. Some more abstract, kind of, Tron sci-fi stuff. And I'm showing here that you can make things that aren't organic as well using implicit functions. Right? That happens to be part of the payoff, so that they can represent them. But they can represent hard edge surfaces very well. And then Callie is another one of the sort of masters of the demo scene. So this is a combination of several techniques. So there's these sort of smooth implicit surface blobs, and then on top of that there's some fractals, and the fractals are mirrored in interesting ways. Sort of lit, art directed, with all kinds of good stuff. So that's our inspiration, those kind of things. So this is all on the Shadertoy website. And the links to those specific ones I showed are going to be in the top slides as well, so you can see those. The reason I mention that is that's the tool that I'm using today to create all the content. And so I want you to be aware of it and sort of look for inspiration there. There's also, in addition to this talk, there are sort of 2 classic tutorials. So one is by Inigo, another one is by Fabrice, who's a professor in France, but who also by night likes to hack amazing things online. And then not as impressive as their things, but sort of designed to get you into it a little more smoothly. I made these 3 examples of showing you how you do implicit surfaces, and taking a fractal and showing you how do you get fractal content in instead of noise function. Okay. Questions on everything so far, because now I'm going to actually get to what I promised you, which is something make a plan. Okay.
I've never seen sliders in Shadertoy before. You have to tell me later where you got, how you made them appear.
Oh, I have a plugin for Chrome that like hacks it and adds some stuff that makes things
Very good.
So you mentioned that in order to create something like this, you want something that you kind of unexpected. So how you gonna, let's say I'm an artist, I already have something in my mind. Right?
Yeah.
So how am I gonna be able to create something like this? Do you have some kind of DSL or domain specific?
Yeah, that's a great question. So what if I am an artist, right? Like I'm not an artist, so I'm trying to do this without an artist. But what if I am? And so there's a couple answers. One is that hopefully if you're an artist, you have a good friend who's a programmer. And that programmer is going to create this content, so instead of taking a noise function, it's more like GoGAN, where there's some input that you can pass in. And maybe that input is primitives, like in the Houdini example I gave. Like the artist can make some, sort of building blocks out of which we build a scene. Or maybe the input is like that GoGAN case, where they're going to paint sort of, well, here's where I want the rivers to go, and here's where I want the mountains, but the details of the mountains will be done. So that's the classic way to do it. And then the new, more machine learning way would be, and there's various this all comes down to choosing the way you represent the geometry. But you can imagine the artist making exemplars, maybe painting concept art, which is what's normally done anyway, saying, well, this is kind of what I want the scene to look like. And if I show you 5 examples, make a program that can generate more by learning from that. Or by creating the actual 3D geometry, or the lighting, or the animation, or the text. And so this is a notion of supervised machine learning. So you provide exemplars, and you try to write a program that can somehow generalize from them. And what's nice about the particular case of not arbitrary content, but sort of the structured content that I'm demoing here, is that it doesn't have to be machine learning from nothing at all. Right? You know roughly the structure of the program, you just don't know what the constants should be. So if the machine learning program has to generate, maybe is not the distance function or completely from scratch, but we give it roughly some functions and say you have to learn how the shape of the mountain should be, but I'm going to tell the program what mountains are in part of the ground.
Then I have the second question, which is, then what is the benefit using the ray tracing on this implicit surface compared to the ray tracing on the explicit surface? So because now you limit the ability of artists to create this kind of content, and if the artists have to go back and create the content with the traditional pipeline using the triangle mesh anyway, then what is the benefit of doing this?
Yeah. So what's the advantage of the implicit versus explicit if there's an artist involved? And the answer is, first of all, I should tell you that you can go between the implicit and explicit representations. You usually lose something, especially if you round trip, you get a little bit of round off. But there's some pretty good algorithms for turning geometry into a signed distance function, and for turning a signed distance function into explicit geometry. For example, the marching cubes algorithm is one of the many ways of going from an implicit to an explicit representation. It's used a lot for fluid simulation. So at render time, especially for a game, like something like Minecraft or No Man's Sky, it uses explicit geometry at runtime for speed. But the content is created implicitly and then it's converted over with various algorithms. And so you're absolutely right that in practice, if you had an artist and you're trying to ship something in production, you'd want the best of both worlds and go back and forth. Dreams for PlayStation 4 is another, by Media Molecule, is another wonderful example of a program that sort of generates with implicit surfaces and then switches to explicit ones. In practice, for anything volumetric, like clouds or fog, which we'll see in a moment, in some cases, even skin or marble, things where light can kind of pass through it a little bit. You have to stay with sort of the ray marching approach that I was describing, that just is the state of the art. But you can kind of accelerate it using explicit geometry to at least bound the volume over which you're going to have to sample an implicit density function. But yes, in production, you would go back and forth. Today, there are no artists up here at least, and so I'm going to stick with just rendering it directly from the implicit representation because that's easier for me. There's no reason to go explicit if I can render it directly.
Then I have the last question. Sorry. What is the intuition behind the random function scenes? Like, let's say one of the slides you have shown that there's so many random functions that you can use for seeding your content generation. Let's say that I want to create a Minecraft world. Then there's so many functions. Which function that I should pick?
So usually, so the Minecraft example is a combination of a biome generation algorithm, which is essentially using a very low frequency noise function that gets rounded off to say, this is a desert, this is going to be grassland, this is a mountain. And then within that region, running a higher frequency noise function. So Minecraft is almost exclusively noise functions. There's a little bit of grammar stuff for generating villages and specific caves and things like that. But sort of how to combine those and stuff, that's exactly the that's the art side of the programming. And to me, that's part of the joy, is finding, like, hey, this function sort of looks like a tree. This function sort of looks like a mountain. And the exponent kind of controls the steepness of the mountain. So we'll see some examples of that maybe will answer that better. Thank you so much. A lot of the stuff, I'm a professor, right? I teach intros, CS, all these kinds of things. So, most of the Shadertoy programs are written by people who are trying to get some code out quickly. And the language that it's in, which is GLSL, does not make it easy for you to abstract things well. But you'll notice in my code that I at least use these sort of C-style macros to give some semblance of readability to the code. So, I don't think my programs, the output is any prettier, but hopefully the program itself is a little bit prettier and in a way that'll help you with things. It's a plea to write your own code that way, even if the language is funny. But here's what I want to do. So I want to make a planet, a tiny Earth-like planet. And the reason I say tiny is that there's sort of a sense of scale, like kind of a Little Prince look to these examples. Right? So I just Googled tiny planet and then started pulling out the images I liked and ignoring the ones I didn't like. And this is sort of a good way to start any game or any content project, because you want lots of exemplars just for yourself to guide you. And this is kind of the, not that I'm a great artist, but this is like great artist style. So you don't have to be super original about everything. And what I'm looking at here is trying to abstract, and this is the key step, is I'm trying to abstract what makes these examples that I like similar to each other and different from all the ones that I didn't put up here. And so there's a couple things that I'm noticing about these. One is the tininess is kind of, it's coming from the sense of scale of the features. The features are too big to be realistic for the size of the planet. Here's a tree. Right? The tree is like bigger than several countries. So that kind of sells the tininess. Another thing is that if you look at the real Earth from space, it doesn't look anything like this. So the real Earth, the atmosphere ends at the atmosphere. It's like not very high compared to the radius of the planet. But these, to give it that friendly, happy look, they all put a blue sky behind the planet. And this one's really explicit. The other ones, they at least fade it out. But so there's this sort of notion of the atmosphere, just like the features, is going to be exaggerated. They're also lit in a way that's sort of like the way you would light a portrait, not the way that planets are really lit. So planets are kind of really bright on one side and completely black on the other. At least if you have a single star planetary system. And these all have like really nice, tasteful lighting, like somebody came in with a little bounce light on, light up the details. So I'm looking at all those kind of features, and I spent a long time making a list of those. I won't drag you through it right now. And then that sort of gets to, here are some of the highlights that we're going to go through. Okay, so that's how I'll make a happy planet. First, I need to have that atmosphere, I need to have oversized features and kind of exaggerate things into it. So here we start with the black screen again. And what I'm going to do this time is I'm going to, instead of making a vertical gradient, which you saw, which is just a function of height for each color, I made it a radial gradient. So based on the distance from the center of the screen, I have some function, and it's going to be kind of bluish. And then my concept art, I noticed that it wasn't uniform. There was sort of this like glowing. And so I'm going to do that by just adding random noise as a function of the angle. Now this looks a little ridiculous towards, like this looks great out here, that's what I want. In here it looks ridiculous, but there's going to be a whole planet right here, so I'm okay with it. And this is the only 2D part of this program. I'm just cheating and drawing this in the background as a 2D thing, because it was easy. And then I have some stars now. And the stars are just another noise function. And you can think of it as, imagine you're looking down on mountains, and then I put a plane and I just clipped off the very top of a couple mountains. So all you see are those little pinpricks of the tops pointing through. And I put some exponents and stuff into it. Okay, so now I get some stars, and they'll twinkle with time. When I stick a planet there to really sell it that the planet is 3D and is like in the middle of this actually 2D backdrop, what I'm going to do is I'm going to darken it by the shadow of the planet, like casting a shadow, but there's no actual shadow, I'm just tweaking the 2D image. So to the extent that this is fake, this is the end of the faking. So I'm just putting this picture in the background because it makes the planet look better, it makes it happy. But everything else I do is going to be actually 3D. You can fly down to the surface and explore it. It's very similar to the Okay, so that's my background. It's very, Star Wars or something like that. So let's take that away for a moment. Here's my planet, and I've defined a distance function, just like I taught you. In this case, starting with the sphere distance function, so it's good. The planet's roughly a sphere. And then all I'm going to do is add some noise functions, but instead of in 2D, I'll define them on the surface of the sphere. And I'll define them in 2 dimensions so they're smooth and there aren't any super sharp clips. So that gives me this. And it's a couple octaves. I think I have 5 octaves of noise here, and I raised it to the 3rd power to make the mountain sort of more peaky. So the numbers closer to 0 get pushed down and it kind of flattens out the base. But that's my mountains. And then I'll do the same trick that I did before of saying, well, I'm going to impose a sea level. And everything that's closer to the center of the planet than sea level, that'll be ocean. I'll raise the surface up and draw a surface, color blue, and I'll keep track of how deep the ocean is there. So I can give you some impression of depth by changing the amount of blue. You're not actually seeing through the water. You're seeing water where the surface of the water is painted based on how deep it is, but it looks right for me. Graphics is fantastic. I could make it transparent if I wanted to. I was being lazy. So I can take the oceans, and I added some little waves in there, a little too small sea wave. Then what I can do is I'll take that same idea, I'll say, well, if it's kind of high, I'll call that a mountain. And so I'll color it brown as a mountain. And you can see I added a little bit of noise into it because I don't want like a perfect line where sort of the beach becomes the mountain. So I wiggled a little bit, but it's basically just one threshold is water, one is mountains. And then I'll take the mountains, and I'll say, well, if it's really high and not too steep, that's going to be ice. And if I'm close to the shore and not too steep, I'll make that sand. So this is the coloring the biomes that we talked about, but I'm doing it based on the noise functions. And then I'll say, well, and if you're kind of at a temperate, nice elevation, and the slope is not too steep, then a tree could grow there, and so I'll color those green for vegetation. And I did a couple other tricks that I didn't explain, like you can see towards the polar regions, I sort of tweaked the function so that things get icier up there, and the water itself changes color a little bit. And I got that by just looking at photographs of the Arctic and noticing, oh, the water looks kind of different. All right, so that's basically it. Like that was the hard work. Everything else is going to be polished to make this look impressive, but that was the magic of procedural surface stuff. And it really was just noise functions and a little bit of intuition about, oh, look at the slope. And the reason I could look at the slope is because I had that function that was differentiable. So the slope I could compute as the gradient. But to impress you that I know computer graphics, I'll put lighting on this. When you put lighting on stuff, it looks amazing. So here I'm doing sort of classic, if you took photography 101, they'd say, well, you put a key light up here, and then you put some other light on the back. It's maybe a little colored or darker. And then there's a light behind it that's a rim light, just kind of to make the outside light up nicely. And I'm also tinting it towards the atmospheric color as I get towards the silhouette, so it'll blend nicely into the halo that I was drawing. Of these lights, I'm computing shadows for the key light. And so the shadows are just casting an extra ray from the surface back up to the light, saying, well, if I see the light, then I'm not in the shadow. And I didn't bother shadowing the fill or the rim light, especially because the rim light's behind it, so everything will be in shadow lines. So then I do the ocean waves. I'm not going to go into detail about the ocean wave simulation. The slides are here, I'm going to skip over them, except to point out something that's really close to my heart because I'm a sailor and I spend a lot of time on oceans and lakes, which is that in the real world, waves always come in with the wave fronts parallel to the shore. You're never standing on the shore and seeing the waves go past you this way or seeing the waves come out from the shore, but they always come into the shore. But what creates the waves is friction between the wind and the water surface. And the reason they get higher and break is because there's friction at the bottom as well, and they get close to shore. So what that means is you're in deep water. The waves have a particular direction, which is the direction the wind's blowing. On my planet, I'm going to blow the wind always around like this, and so deep water waves are always sort of lined up, blowing that way. The reason that the waves are always coming into shore is that friction on the bottom of the ocean, right, as it comes up to shore, that causes refraction in the wave. It causes waves to bend, so they always come into the shore. And there's some really nice math for doing that. It was from a paper from 1984, sort of explain this, and it's essentially, if you love math, this is great. It's this path integral over the sort of 2D manifold of the bottom of the ocean floor with viscosity and all this stuff thrown in. And that's lovely, but there's no way you can compute that quickly because each of those path integrals is a big for loop in every pixel, a really big, like a million-step for loop. But it turns out there's a nice approximation, which is if you assume that the slopes are constant, the ground is falling off at a constant rate underwater, there's a closed form approximation of the integral. And so I'm using that to get the ocean waves because I have this sailor fetish about the waves. That's what these slides are as a spare. Okay. And there's some code. It turns into 2 lines of code. And that's my favorite kind of program. Like going where I write 3 pages of math, and it turns into this tiny little expression I put in the code. It seems like magic if you don't understand where it's coming from, but it's so elegant if you do. All right, well, I want clouds. If my reference art all had clouds in it, and that was part of what made the planet look happy. Clouds don't have a surface, so instead of distance to the surface, you have a density function. So at this point in space, how much stuff is there? And if I make my cloud function constant, I took away the shading so I could see things, and I just get fog all over my cloud, which is, it's a step in the right direction. You can see the mountains which are black, this is no shading, just poking up out of the fog in a couple places. And all I have to do is put some noise into the clouds, and they'll start to look like clouds. So there's my standard noise function. I did the 5th order version of it, so 5 octaves of noise. And I have 2 magic constants that I just moved around until I like the way they look. The density happens to go negative here. At 0 density, there's nothing. At negative density, there's still nothing, but I didn't want the discontinuity because I wanted it to be differential. So don't worry about the negative density. That's just sort of there to make the math work out. But there's my clouds. And I was kind of happy with these clouds. I actually had the clouds like this for a while. And then I looked back at the reference art and I thought, real clouds don't look like that. Real clouds are like very swirly and dramatic. So there's a trick to make these fractal Brownian motion value noise systems swirly, which is you run the output, you feed it back into the input again. And every time you do that, you get another level of vorticity. So I just take the function, and in this case, just to make it cheaper, I hit 3rd order, and I stuck it in, and then I feed that into a 5th order noise. And that makes the clouds kind of swirl in interesting ways. And then I can make everything a function of time, and the clouds will evolve. Let's put it all together. So here's my background. Stick in the planet, the shadow, and then I put the clouds on top. It looks like that. And just like with the Greek island example at the beginning, what's super cool about this is, I tuned it looking at that particular view, but there's a whole planet there. And so the planet turns around, or I can cause it to turn around more quickly. And there's all kinds of stuff that I didn't plan that's right on the backside. And by changing those constants, I can create totally different planets. I create planets with no water, planets that are all water, planets that have different rules for where vegetation grows. Maybe it likes to be enclosed. Mine doesn't. Maybe the clouds are 2 different layers of atmosphere. So you can sort of play with all of that stuff. So this example is online. There's a little bit of post-processing I'm doing in 2D afterwards to make the images look even better. And you can see that kind of documented in my code because I wrote all those nice comments for it. Let me wrap up. I promised you that you could apply for a job at NVIDIA as well. So if you go to this URL, which you can remember as the name of the institution you're at, so nvidia.com/university, and that's a listing of all the job internships. There are many in Toronto. There are many around the world. Finland, China, California, wherever you want to go. And I should also mention that NVIDIA does graphics, I do graphics, but there's an awful lot of stuff that's not graphics. This is a company that makes complete systems, so there's huge amounts of work on robotics, on AI, on machine learning. We create compilers, we do physical simulation. There's lots of stuff that goes into how do you build processors and design them, how do you design new kinds of semiconductors, memory systems. So essentially, anything that ends in something engineering or something science, there's a corresponding thing going on in NVIDIA. They encourage you to look at that. So to summarize what we saw today, there's procedural content, you create the rules, and the rules create the art for you. There's kind of this three-step process, and the interesting thing is understanding all the different values you put into this process. And it's an iterative process. I showed it to you as if it was coming perfectly fully formed out of my head. I mostly knew the guidelines for the techniques I was using, but the constants I was tuning and going back and saying, oh, what if I use a different noise function? What if I hash it in a different way? And that was the fun part, is the iteration. And that's sort of the being an artist from an algorithmic perspective. And we talked a little bit about different ways of ray tracing. But then when I actually made the planet, I think the most important step was the art direction step. It was really looking at examples that were hand-created by artists and trying to understand and mathematically abstract what they were doing. That's the part that maybe machine learning would do for us someday, or maybe actually that's the interesting part of algorithm design. Humans will do that with these tools in a different way. It wasn't just the geometry. I focused on that. There was some stuff with materials, the animation, lighting. The key technique I use a lot today is called fractal Brownian motion applied to value noise. Those are sort of the things you would Google to find out more about it. And then there was a little bit of post-processing that I promised you was online, but I'm not going to go into now. And just like I said, you can do variations on the theme. I just searched on Shadertoy for tiny planet. And I'm not the only one who likes it. So there are lots of examples, and they're structurally extremely similar to mine. And it really is just a matter of changing the palette, a few constants, or use this out. But we're all using the same underlying pieces of math, just combining them in ways that are creative. So hopefully I'll see your slide later. So, thank you very much. Since we started late, why don't we let the audience go, but I'll be happy to stay up here and answer questions for anyone else.